Hello and welcome to Snippets for Statistics. Today's lesson is on the chi-square goodness of fit test. So what is the chi-square test of goodness of fit? It's a non-parametric test, and that means it doesn't involve parameters such as mu or rho. It doesn't use numerical scores. We're going to be looking at data as frequencies. It relies on the chi-square statistic. It uses sample data. It does not state the hypothesis in terms of a specific parameter. As we mentioned, we don't use parameters. Instead, it states general hypotheses about the entire population. It does not reference specific population parameters, and it makes few, if any, assumptions about the population distribution. We have two types of null hypotheses for the test of goodness of fit. One is that there is no preference among the different options. They're equal probabilities. The second type of null hypothesis is that there's no difference from a comparison population. That is, we are looking at a population that has a specific distribution, and we're saying that for the null hypothesis, our distribution has the same distribution as theirs. So the strategy is, we use the null hypothesis to generate a set of expected frequencies for each category. Then we collect a sample. That becomes a set of observed frequencies. The chi-square statistic determines how well our observed frequencies fit the hypotheses by looking at the differences between the scores. Here's the formula. Chi-square, and there's the symbol for chi-square, equals the sum of the square differences between each observed frequency and expected frequency in each category over the expected frequency for that category. So here's an example, a sunny day experiment. Joey wanted to find out which type of lemonade people preferred. He had two types, homemade and store-bought. He set up a stand and asked each of the 10 customers who came by which type of lemonade they preferred. They wrote down their preferences on a piece of paper. Here they come. Okay. So Joey expected there to be no preference between the store-bought and homemade lemonade. That meant that he expected to find an equal number of people in each group. If we have two groups, the expected frequencies will each be 50%. If there had been three groups, they each would have been 33 1/3%, four groups 25%, and so on. If the null hypothesis is correct, then 50% of 10 equals 0.5 times 10 equals 5 individuals will choose store-bought, and 50% of 10, again, 0.5 times 10 equals 5 individuals will choose homemade. We use the formula expected frequency equals, we use the symbol F sub E, equals P times N. P is the probability or percent times N, which is the number. As we can see here, there's our null hypothesis. This is what he observed. The H's represent homemade, S is store-bought. So, store-bought, what he observed, was that store-bought, only 2 people preferred that and 8 people preferred homemade. So, if we now fill in the table as follows, we get store-bought, 5 people were expected to prefer store-bought and 5 people were expected to prefer homemade. However, only 2 preferred store-bought and 8 preferred homemade. Using the formula chi-square equals the sum of the square difference between the observed and expected frequencies over the expected frequency, we do that for each category. So we look at 2 minus 5 squared. That's 2 from the observed category for store-bought minus 5 from the expected category in store-bought, and we square that, put that over 5, which is the expected value. And then we add the homemade column, which is 8 from the observed category minus 5, and we square that and put that over 5. We add that up, and that gets 3.6. Note that our degrees of freedom are C minus 1, where C is the number of categories. If we want to determine whether our observed sample fits our expected hypothesis, then what we do is we compare our chi-square obtained, that's what we got when we did our calculation, with chi-square critical, which we find in the appendix in Graviter and Wallnow, or our textbook, for our determined alpha level. And then we make a decision. So we're going to use alpha equals 0.05 with two categories. Therefore, degrees of freedom equals C minus 1 equals 2 minus 1, which is 1. And the chi-square critical is 3.84. Since our chi-square obtained is not more extreme than chi-square critical, we cannot reject null hypothesis and must conclude there is no preference. We would probably consider with an experiment like this that our n is way too low to really get good data. But this gives us an example of how we walk through a chi-square goodness of fit test and make a decision based on our observed data as compared to our hypothesis. And that concludes our Snippets for Statistics chi-square goodness of fit test.